Hey everyone. Okay, so when you're dealing with a low density gas, then what you'll observe is either an emission or an absorption spectrum, right? When the gas is hot, then that hot gas has enough energy that it can excite some of the electrons. It can make the electrons jump up into higher energy levels, which they will last. They'll last at a higher energy for a little while, seconds to minutes usually. And then eventually that electron will de-excite, it'll settle back down into a lower energy level, and the electron will lose energy. And it will lose energy by emitting a photon. Right? So the electron drops down, and it does so by giving off light. And so your hot cloud of gas will shine with those emission lines, and the colors that can be emitted depend on what element the atom is made of. If you have a cool gas, then your electrons start out at low energy levels, which means that if a photon comes in, right, then the photon comes in, the electron absorbs that photon, it gains that photon's energy, and the electron jumps up to the higher energy level. And so, if the light shines through this cold gas, then the spectrum of light that you will see will be all the colors of the rainbow emitted by your original continuous spectrum, except for that light that got absorbed by the low-density cool gas in between you and the black body. And so you'll see those dark lines missing from the spectrum, missing because those are the specific elements, those are the specific wavelengths that the electron absorbed. And so you'll see, if you plot this spectrum on the graph, then you'll see your continuous spectrum, right? Your usual black body spectrum, except for those little dips where the light got absorbed by the cool gas in the foreground. So, which of these atoms will make an emission spectrum? Well, you emit light by losing energy, when the electron loses energy. So the electron loses energy, shoots out the light, it emits the light. That gives you your emission spectrum. What gives you an absorption spectrum? Well, what gives you an absorption spectrum is when the electron absorbs light, and the electron will absorb light in order to jump up to the higher energy level. So, there you go. What type of spectrum is produced by a hot, dense object? Well, that's a continuous spectrum, or a blackbody spectrum. Two names for the same thing. What type of spectrum is made by the hot diffuse object, the hot diffuse gas? Well, if the gas is hot, then that hot gas has enough energy that it can emit light. If you have a hot dense object producing a continuous spectrum, but then that continuous spectrum is shining through a cool gas, that cool gas is at a low energy, so it's in a good position to absorb light. Hence, you see an absorption spectrum. What type of spectrum is made by a star? Well, a star has a hot, dense core, and so the light given off by the core is a continuous spectrum, but then at the surface of a star, you get a cool, low-density atmosphere, and so as the light from the core shines through that cool, low-density atmosphere, the atmosphere will absorb some of the light, and so you'll get an absorption spectrum. So that's what you get from stars like the sun, is you see an absorption spectrum. All right. Using our library of known spectra here on page 59, here on the next page, what element must be in the atmosphere of this star? Well, we're getting a continuous spectrum, except for these missing lines. So let's start from the red end. Let's start from the right-hand side here. And we say, okay, there's a line at this wavelength, And what is that? That looks like, well, if this line here is 655, sorry, if this is 650, and it looks like there are 10 tick marks between 600 and 650. So that means that each tick mark must represent 5 nanometers. So then this line looks like it's at 655 nanometers. What element do we know of has an absorption line at 655 nanometers? No. That looks like it's more like 660, so probably not that one. Nope, that's too much. That looks good. Okay, so it looks like hydrogen looks good. Iron, no, that's 650, not 655. That's too low. Nothing in the red. Titanium, nothing in the red. Water also looks like it's 660. So I think the only one that looks like it's at 655 is hydrogen. But how do we know for sure? Well, we know that there's hydrogen in our star if it has all of the hydrogen absorption lines, right? We can't pick and choose. If there's hydrogen in this star, then we have to see all the hydrogen absorption lines. This one in the red, this one in the green, and these two in the blue. Okay? Is there all 4 of those lines in this spectrum? Sure enough. This one in the red, the one in the green, the 2 in the blue. All right, so hydrogen is the element we're looking at here. Okay. How about here? Got a lot more lines over here. So is there an element, let's see, is there an element that gives us all 3 of these red lines? No. Okay. So if there isn't one element giving us all of these lines, right? There's none of our spectra here have all the lines that we're seeing in that star. So if it's not one element, then it must be more than one. There must be more than one element giving us all of these lines. There must be a mixture, because if you have more than one element in your gas, then you're going to get all the lines from all the gases that there are present. So we must be looking at more than one element making this more complex spectra. How do we do this? Well, again, let's start from the red end and work our way toward the violet end. This line right here looks like it's at what? Let's see, 650, 55, 60, 55, 60, 65, 70? This one looks like it's something like 670. We're pretty close to it. So what element do we know of has this line here at 670 nanometers? No, carbon's at 660. Looks like helium. Okay, so I would guess, and is there any other option? Not really here. Nope, not really. Okay, so seems like helium is our best guess. I would guess that if we're seeing this line at 670, there's probably helium in this star. But how do we know for sure? We know there's helium if all 4 of these lines are in the spectrum. So let's check here. All right. All right. So this is helium. This line here at what is that? 590. It looks like. Yep. Sure enough. So this one's from helium. This is from helium. The next line is at about 500. So right there. Okay. That's helium. And the last one is 495. Sorry, 445. Let's see. So 445. There it is. Okay. So all of the helium lines are in this star's spectrum, so there must be helium in this star. All right. Now let's go back to the beginning. Now there's a line at 655. So what element do we know of has a line at 655? Well, hydrogen was our best bet before, so I would bet that there's hydrogen right there, that's a hydrogen line. How do we know for sure? We have to see all the hydrogen lines. So, let's see, this one here. Now this one at, 500, 495, 490, 485. Okay, so there must be that green line at 485. 500, 485. Okay, there we go. So there's the line, there's the hydrogen line at 485. And then, 450, 440, 435. Okay, 435, 450, 40, 435. 1, 2, 3. Okay, it's that one there. Okay, there's the hydrogen line at 435. And then this last one at 410. All right, there we go. 1, 2. Okay. So all the hydrogen lines are here. So we know that this star is hydrogen and helium. Do we have all the lines accounted for? No, not yet. All right, so we must not have all the elements figured out. So let's go back to red and say, all right, how about this line here at 650? What element do we know of that has an absorption line at 650? Nope. Nope, that's 650's right there. Nope. Nope. Okay. That one right there. All right. Anything else? No. Water? No. Okay, so I think iron's our best bet here. So if this line is an iron line, then there must be these three in the green. Ah, there we go. Okay, so those three are also from iron. And then these two in the blue, this one at 440 and 435. Okay, there we go. Those two right there. And you might think that line right there we already have accounted for from the hydrogen. But notice that line right there is a thicker line. So why is that line thicker than it looks over here? Because that's probably two lines right next to each other. This hydrogen line and this iron line. So both of these lines are from iron. And instead of one thick line, the iron line and the hydrogen line are basically right next to each other. And so it looks like one fat line in our spectra. And then the last line is this big thick one here at 405, it looks like, right? And then, is it there? Sure enough, there it is. That iron line at 405. So sometimes an absorption line is a big thick line that is really good at absorbing a lot of light, like this one is right here. Sometimes you've got two thin lines, but if they're stacked up right next to each other, then it'll look like one thick line in your spectra. So, okay, do we have all of our lines accounted for? And are there any lines we haven't explained? Yep, we got them all. Okay, so if we have all of our lines explained by coming from helium, hydrogen, and iron, then this star must be made of hydrogen, helium, and iron. All right, mystery solved. All right, so this is how we figure out what stars are made of, right? Look at all the lines and start from one side. We didn't have to start from the red. We could have started from the violet side if we wanted to. Start from one end and just start marking off the lines based on what element they're made by until you have all the lines explained, and then you must be done. We figured out the full composition of these two stars. This one's just hydrogen. This one's made of hydrogen, helium, and iron. That's how you do it. All right. Hopefully that makes some sense. And if that's making sense, then you're ready to go on to the torus lesson, and you'll get a little more practice there on torus. Okay? All right. Post your questions to the discussion if you've got them. Otherwise, see you later.